In another video, we looked at a method of studying radioactive decay using a charged balloon. The daughter products of radon decay adhered to the balloon. These daughter products were themselves radioactive, and we used a Geiger-Müller tube and counter to measure emissions. As more than one different radioactive element was present at any one time, this experiment could not be used to find half-life. Here we look at 3 commercially available radioactive sources that can be used to find the half-life of an element. They are currently the only ones approved for use in Scottish schools. First off is the Protactinium Generator. Then we have the Eluting source, also known as the Isotope Generator. Finally, we have the Kuchnel ionization chamber. The Protactinium Generator contains uranyl nitrate. About 1.5 grams is mixed with hydrochloric acid and hexyl ethanoate. Protactinium is one of the decay products of uranium-238. It decays by beta emission to uranium-234. Hexyl ethanoate is immiscible with water. Left alone, it will form a layer above the hydrochloric acid. The protactinium is taken up by the hexyl ethanoate. If the generator is carefully shaken over a tray and placed upside down, protactinium will end up in the hexyl ethanoate layer at the top, where the protactinium decays. For good results, take counts over 10 seconds. Ignore the first reading. If a data logger is not available, you may have to miss out alternate readings in order to have time to note the reading and reset the counter. Continue for at least 6 minutes. 15 minutes after starting to collect data, measure the count rate over 10 seconds 4 times and take an average. This figure should be used to correct the count rate. Normally, we wouldn't take a background count reading with the source in place, but in this case we have to, because there will always be other elements decaying in the generator, not just protactinium. Note the perspex shield, necessary because we are dealing with beta radiation here. Every half-life source has advantages and disadvantages. In the case of the protactinium generator, the advantage is that it is relatively cheap to buy. Now you may find make your own recipes online. Please do not under any circumstances try this. There are a number of disadvantages to the protactinium generator. After 8 years, you'll have to pay to have it disposed of, and this could be costly. It is hard for students to understand how it works, and the contents are hazardous for a number of reasons. And though a spill is unlikely if you follow SSERC guidance, it could be problematic if a bottle ruptures. The barium eluting source or isotope generator contains beads impregnated with radioactive cesium-137. Cesium-137 decays to barium-137 by beta emission. An isomer of barium is formed. The nucleus of an isomer is in an excited state. A special liquid is passed through the generator, removing the barium but not the cesium. This washing out process is called elution. The barium in a liquid decays by gamma emission to stable barium. The half-life of the barium isomer is 2.6 minutes. If we place a detector close to the liquid and take counts over 60 seconds, we should be able to plot a decay curve from which half-life can be found. Background readings should be taken before the experiment in order to correct the count rate. Between a quarter and half an hour after the elution has been made, the activity of the liquid should have returned to background levels. If it does not, it could be that some cesium has bled through. Once again, there are advantages and disadvantages to using this source. Though the eluting process may look a bit fiddly, what we have is a radioactive liquid that becomes less so with time, reaching background levels after half an hour. This means that any spills can simply be left until they are no longer radioactive. The drum itself could break, releasing cesium, but this is very unlikely. It is expensive to buy, and eventually you will need new eluting fluid, but it should be long-lasting. The third half-life source permitted for use in Scottish schools is the Thoriated Gas Mantle used with the Kuchnel ionization chamber. The bottle contains 4 gas mantles that have been impregnated with thorium. Radon 220 is part of the thorium decay series. It's a radioactive gas that decays by alpha emission to polonium 216 with a half-life of 56 seconds. The radon can be squeezed from the bottle where it accumulates into an ionization chamber. There is a tiny current in the chamber due to ionization. This is amplified and the output is a voltage that can be read from a meter or recorded by a data logger. We suggest taking 6 readings per minute. The advantages of this source is that it's relatively cheap to buy. A lot of legislation doesn't apply to it, but you do have to follow our risk assessment. There's no need for a specialist detector. A voltmeter or data logger would be fine, and the source also blocks out most of the background radiation. Its only real disadvantage is that it can appear to be something of a black box. Students don't know what's going on in there. So all of these methods have their own advantages and disadvantages. What we haven't mentioned in this video is much about safety. Please get in touch or visit the Physics, Health and Safety section of our website to find out more.